Good morning. It's great to be here. It's a great honor to speak about the impact that JWST has on our field and beyond. I'm going to continue on the topic following excellent talks this morning, focusing on a specific aspect of protostars, outflows, jets, and planet-forming disks. Just to quickly indeed focus, we're going to look at this early stage, first roughly 500,000 years of star formation process. This is a very interesting stage where most of the action happens. We have most of the mass is already assembled onto the star, and we also start forming building blocks of planets. So there are several physical components. Those young systems are very complex in terms of physical structures, and we're trying to disentangle that a bit. And following talks that were focused on the absorption features, I'm actually going to focus on emission lines. What can they tell us about those systems? And infrared is really crucial regime to study those protostars because they are still very much hidden into the envelopes from which they form. And JWST has been great in illuminating those processes. We look here at the optical image from the ground of one of the forming stars, HH46. And as we look in with near-cam image of JWST, it clearly shows us what's happening inside the stunning stellar fireworks revealed by the outflows. But outflows are much more than that. They're much more than just a beautiful spectacle on the sky. They actually carry a lot of useful information. Apart from they are a first birth cry that we see of a newborn star that we can already see in optical, but we can also retrieve wealth of information about how those systems are being born. And as we look through more spectacular near-cam images, I'm going to tell you some of the key interesting aspects of outflows. So they release angular momentum. So in principle, they actually enable the accretion to continue because as the envelope is spinning faster and faster as it collapses, it allows the accretion process to continue by releasing some of that excess spin from the system. And additionally, as we look into this beautiful protostar in Orion and its outflow, you can notice a lot of bullets, we call them, or knots of emission. So those are actually related to the episodicity of the accretion process itself. So in a sense, the jets carry the fossil record of the star formation history of the recent years of what's happened in those regions that are still very hidden from us. And indeed, those jets, as they release the material from the system, they allow us to conclude what's happening on the inside, both in terms of physics, what kind of accretion history happened, but also in terms of chemistry, what is the content of the regions. That is in the case in here, in HH211 in Perseus, we actually, even for JWST, the central protostar is still very hidden in this cloud of dust and gas when it's formed. So we can use the jets to indirectly understand what is the composition of the innermost region, where actually the building blocks of planets are already being formed. So to summarize, there are a couple of very interesting aspects of jets and outflows that we want to understand and what we can do with JWST. I will focus on that now. Just to highlight that ALMA, another powerful telescope that we have on the Atacama Desert, the radio telescope, has been essential in the past decade to help us understand those outflows. However, it mostly probes the colder molecular gas in those outflows, but it's practically blind to the ionized and atomic content, the hotter component of those outflows. And the nice example of that comes one of the programs I'm going to talk about today. This is IPA, so this is an open time program to study protostellar accretion. And we selected 5 protostars at different luminosities, which also means they will end up forming different mass of a protostar from very low mass to high mass protostar. And the lowest mass example here is actually very interesting. So if you look on the left, we see ALMA image here in the molecular cold gas. And we see there is no central jet, the spine that would drive this whole flow. We only see the cold molecular, actually carbon monoxide around it. But if you look with MIRI and NIRSPEC on the right, we see that there is a certain jet, but it's completely atomic ionized. So that's why we couldn't see anything with ALMA. So it reveals how the combination of the two allow us to probe the complete structure and complete composition of those jets. You can also see that the images are a bit different than spectacular near-cam image. This is because we're now looking at integrated field unit, which maybe doesn't provide such spectacular images, but it's extremely rich because each of those pixels contains also spectral information. That's why we can identify those lines so clearly. Another example, a contrasting example actually, is HH211. This is an extremely young protostar, probably as young as several thousand years old since it starts forming. And we already knew this one has a molecular jet because it was revealed by ALMA, but JWST provides another layer to those features, showing nicely corresponding molecular gas. And actually here, James Webb also sees molecular hydrogen and carbon monoxide. And as image can only tell part of the story, if we look at the spectra, what we actually see that there's a wealth of molecular lines, but very little ionized content. So this jet is very different than the one that you just showed previously. So what could be the origin of those differences? And the answer to that can come from evolution. So since another very successful mission of ESA, Herschel, we had this picture of outflow evolution since very young outflows are mostly molecular and they slowly progress to more ionized and atomic state. But this doesn't really hold for these systems because they are both extremely young. So what is happening? Another idea could be that actually, if we think about this process in terms of evolution, what also changes within the evolution of a protostar is that this accretion rate really decreases. So maybe what we are looking at here is not two sources at different ages, but two sources at different accretion rate. Because chemically what happens is that we have those young, very powerful outflows from very high accretion rates. They also release a lot of material. And in these dense jets, a lot of molecules can form very efficiently. But as soon as the accretion rate drops, also the ejection rate drops, we have much more transparent jets, which are also more susceptible to UV radiation, which probably enables the atomic ionized jet to form. So it's very interesting to see that the accretion has such an important impact also on the outflow process. And I have another excellent example on that, because those two protostars I just showed are from very different regions. But how do we explain differences in protostars that are literally twins? And this data comes from the JOICE program. So this is a GTO program that provides the largest sample of protostars JWST is going to observe in its first cycles. And we observe in general over 20 low and high mass protostars, and the focus will be on one of them, TMC1. So this one is hidden in the torus molecular cloud, and Herschel already revealed a power bright point source in the center. And ALMA, as you can see on the right, revealed a binary protostar. So those on the white contours are two young disks forming together in less than 100 AU separation. So I can imagine if we had another star just outside our solar system, this is how those protostars are formed. And we saw with ALMA already the molecular flow, which you see in blue and red. This is because of the velocities. And we also see in contours already some infalling gas. So there's another aspect of the story that I'm already spoilering at. But what we see with JWST, this is now MIRI, IFU units. So again, those beautiful maps that each of the pixel reveals with a spectra, so we can precisely identify which species are tracing what in those systems. And we found to our surprise that the source on the left launches mostly molecular hydrogen outflow, actually what looks like a disk wind because to this opening wide angle. And on the right, the source on the right shows mostly atomic ionized jet. So what can be origin of the differences? It's not H because those are basically twins. They form at the same time from the same disk. So the hints from that come again from ALMA, which traces infalling gas, much colder gas, and it sees this infalling cold flow onto the system, and what apparently seems to be infalling onto the left component. So probably what happens, we fuel a lot of this gas into the system, which powers then this prominent disk wind. On the other hand, the source on the right doesn't have this flow, but what it has is an accretion feature, which we can detect with MIRI, that shows hydrogen recombination lines, which come from material from the disk infalling onto the protostar, forming accretion shock onto the star itself, where we see these prominent hydrogen lines. And we can see the red and blue spectra come from right and left protostars, respectively. And we can see that the right one has much stronger accretion from the disk to the star, And this is probably what's responsible for this brighter jet. In summary, this is, again, another example how accretion and ejection are clearly linked, and how using data from different telescopes can tell us the full story on those systems. We have also upcoming very exciting data from another source from the JOICE program. This is BHR-71, spectacular outflow, which in a single source show both this white molecular hydrogen outflow and very collimated ionized jet. What's particularly interesting about this one is we discovered wealth of refractory material there. So refractory material basically in a regular interstellar medium typically appears on the grains. So seeing it prominently in this jet in the gas phase reveals to us that a lot of those grains have been already destroyed, and it enables us to look into the content of the grains in the inner. So if we think about the kind of a cartoonish representation of the system, we have a disk, and very close to the protostar, dust already sublimates because of the high temperatures. And then as the jet flows, it releases a lot of those molecules and atoms that have been released from the grains for us to see. And so it reveals very exciting possibility to study the inner disk indirectly by the use of jets. There are a couple of more examples of outflows that we studied that I'm going to quickly highlight. This is an example of a high mass source, which also shows that we can now look into the much further systems and reveal its complexity. We have a multiple protostars here, and also prominent gas and ice features and gas emission features. And another example from the CORINOS program, which reveals nicely how we can map the molecular hydrogen. We can map also the physical structure of the outflow, how the temperature decreases as we move further away from the protostar. This is again enabled by the ability of MIRI to map spectrally those systems. But moving back to the tracing the inner disk, so I said we can probe them indirectly with jets, but we also have some direct methods to do so with MIRI, which enables us to see the hot gas, molecular gas that's likely coming from the inner disk. And this is again from the CORINOS project, or from one of their young protostars. This is showing that the CO, the carbon monoxide molecule, is emitting at around 1000 Kelvin gas, which clearly shows that it should be coming from this inner region where the temperatures are very high. While on the other hand, the water seems to be tracing somewhat colder material, probably coming from the more extended envelope. And there's another work from JOICE by Logan Francis, where we discovered a lot of simple organics in those disks, in this case from a high mass protostar. And in this case, it's a bit more complicated because we don't have such high resolution because the system is located further away. So it's still possible that a lot of this material can be coming from outflow, but it seems, the temperature seems that it should be coming from this warm disk, but it's not clear if it's coming from the inner or a bit more outside of this disk. And a very exciting case of discovery, which we found in a low mass protostar, was SO2. So that was the first secure detection in mid-infrared of this molecule in a low mass protostar. And this was exciting for us because SO2, we typically associate sulfur-bearing molecules with accretion shocks. So we thought maybe this is tracing accretion shock, but in this case, it seems it's actually tracing the material that's being heated up by a protostar. In any case, it reveals very exciting possibility to study the warm disk with MIRI. And this is still work in progress, but what we are seeming to see, and this also corresponding to the talks we're going to hear tomorrow about older disks, we definitely have some differences between young and older disks. And having all those samples that I just presented, it will be a very powerful diagnostic of how the disks evolve and how they affect the planet formation that's happening inside. So to summarize, JWST has incredible potential to transform our field. And I think the key lies in how complementary it is to the facilities that already exist, such as ALMA. And I think only with them all together, we do have a complete picture of the protostellar systems. And inner regions of young disks can be accessed now with JWST both directly through the warm gas or indirectly by means of outsourcing jets. And I think what we're going to build with the samples is a very nice evolution track of the disks at the onset of planet formation. And with that, thank you for your attention.